A very good evening to you all, and welcome to today's session, today's class, our CCNA 1 instructor training. We'll be looking at Module 5 and Module 6 today. Module 5 and Module 6 are the shortest or briefest modules or chapters in CCNA 1. And that is why I am combining Module 5 and 6. In fact, I wanted to add Module 7, but I felt it would be too much to consume in a day. All right, so let's go into it. Module 5 is basically talking about a number system. Module 5 is talking about number system. Okay, just a minute. So sorry about the brief disruption. So, number system. Number system, we're going to be looking at the concept of binary numbers and then hexadecimal numbers. And you may wish to find out, why are we looking at the concept of number system? And the lecture is about networking. We're going to soon start talking about IP addressing and subnetting. And IP addressing is based on binary. Okay, we're going to be looking at binary. And then that's for IP version 4 and IP version 6. And when we get to IP version 6 properly, we'll also be looking at it in the form of hexadecimal. So we'll be looking at binary, decimal, and hexadecimal. And we'll look at a little bit of calculation between them, okay, or conversion. Now, binary numbers consist of zeros and ones, called bits, okay? Decimal number system consists of digits 0 through 9. Now, host servers are network equipment using binary addressing to identify each other, and that is where the concept of IP addressing comes into being. Each address is made up of a string of 32 bits of binary digits, because we believe that every device that must belong to a network must be identified. It must have its own identity in form of an IP address. And so that IP address is in binary and it carries 32 bits for IP version 4. And that 32 bits is divided into 4 sections, okay? That 32 bits is divided into 4 sections or 4 octets. And each octet contains 8 bits, all right? 8 bits separated by a dot. So for ease of use, this dotted notation is converted into decimal. So the IP addressing that we do convert into decimal is just for ease of use. When you see an IP address 192.168.1.1, okay, it's just for ease of use, but mostly what is being used is in binary, okay? So the key elements we are to take note here is number 1, every device requires an IP address in order to belong to a network. Number 2, that IP address is a 32-bit binary digit for IP version 4. For IP version 6 is going to be 128 bits. We will talk about that when we get to that bridge. But for IP version 4 is 32 bit. And this 32 bit is divided into 4 octets. Each octet has 8 bits. Okay? It has 8 bits. So let's move on. Positioning notation means that a digit represents different values depending on the position the digit occupies in the sequence of numbers, because we want to position binary bits, all right? And the reason for this positioning of this binary notation is so that we can do conversion. Conversion is we want to convert it to decimal. Remember, we said that the idea of using it into decimal is just to help us to be able to understand or the concept of IP address and get the IP numbers to remember them easily. Okay, so we have them in binary and we need to convert them to decimal. So we need this notation. So the decimal position notation system operates as you can see in the table. Okay, there are two tables here. One, you see it in like blue color. The other one, you see it is in like reddish color. Now, the one in like blue color, there are three elements you need to know here. Number one is the position in the number. We call it the radix. Okay. Then in the position of the number, what are we looking at? You see, you start counting from back. This is 0, 1, 2, 3. So you count from right to left. Okay. You count from right to left. What are you actually counting? What are you counting? We're going to explain to you very, very soon. There are certain digits that you want to count. For instance, you have a binary value represented. So you need to count, you need to do the conversion for you to do the conversion, you need to do some counting. So all you just need to do is that notice that position number starts counting from right to left. Okay. Now, the next element that you understand is when they say you are to calculate, you are calculating the value based on the base notation. All right, so you say this is 10 raised to the power of 0. This is 10 raised to the power of 1. This is 10 raised to the power of 2. This is 10 raised to the power of 3. Why are we doing this? To give us these decimal values. This is 1, this is 10, this is 100, this is 1,000, and so on and so forth. Now, bringing it to this table, what does it actually tell us and how do we do the calculation? It tells us that if I pick this position value here, 1,110 and 1, look at it here, okay? If I put it, it means that converting is just to multiply 1 times 1,000, 2 times 100, 3 times 10, 4 times 1. Where are we getting the 1, 2, 3, 4? Where are we getting it? That is a very important question. Where are we getting the 1, 2, 3, 4? It is very, very simple. You are doing the multiplication based on the decimal number here, right? Then once you evaluate it, it brings you to this. I know sometimes it may look a little bit confusing, but I'm going to now do another one that will make you understand, and you will see the meaning. You will understand it very easy. This is another one. This time around, we're using binary. This one, we're using base 10. When you see the radix number, that is the base number. We're using base 10 here. Okay. Here, we're using the radix number 2. We're using base 2. Okay. We're using base 2. Now, once we are using base 2, what do we want to achieve? We want to achieve the position value. And this is the position value we want to achieve. And I will explain that again very soon. Okay. So if I have this base 2, look at it. This is 1, 2, 3, 4, 5, 6, 7, 8. Why are we counting up to 8? Because we said an IP address has 32 bits. So 1, 2, 3, 4, 5, 6, 7, 8. Then there's a full stop. 1, 2, 3, 4, 5, 6, 7, 8. There's a full stop. That's another octet. 1, 2, 3, 4, 5, 6, 7, 8. There's a full stop. Then 1, 2, 3, 4, 5, 6, 7, 8. That is the IP address. It has 4 octets. Each one has 8 bits. You see, there are 8 bits here, there are 8 bits here, there are 8 bits here, there are 8 bits here. And what we want to do is we want to see if there is a way we can easily understand how to do this calculating from binary to decimal and so on and so forth. And then you will now see the value of it very soon. So we are having 8 bits here because it is the number of bits that you have in an octet. So here we want to find out from base 2. Just count from here. This is 1. That is the first one here, 1. Then 1, the next one is 2. This one here. And it's not the number 2, is the raised to the power. How did we get to the power? Just number it. This is 0, 1, 2, 3, 4, 5, 6, and 7. You just number the powers, and that is why you see it here. This one here. This is the same thing here I just did here. You just number the powers from 0 to 7. You are numbering each of the bits. There are 8 bits in an octet, so you number them. So after numbering them, if you evaluate or you calculate, this is what you get. The first bit will be 1, the second one will be 2, the third one will be 4, 8, 16, 32, 64, 128. So observe something. Each one is like double of the other. Double of 1 will give you 2. Double of 2 will give you 4. Double of 4 will give you 8. Double of 8 will give you 16. Double of 16 will give you 32. Double of 32 will give you 64. Double of 64 will give you 128. That is just what we are representing. So, which means that in each bit, these values are represented this way. So if I have a binary number, let's say I have a binary number like this, and I want to convert it to decimal. This binary number that I have like this, look at it, 1, 1, then all through zeros. So I represent it in the same bit value. So you see, this is 1, 1, then the remaining as 0. How do I then convert it to decimal? Okay, it's very simple. I just use my position values that are here. These are going to be constants. They are not going to be changing. They are constants, irrespective of whatever I use. They are constant. So I just put in my values here. Once I put them, then I calculate. Okay? All right. Please, can we just mute you? Right? So I just calculate. How did I calculate? 1 times this 1 times this 128. All right? 1 times 64. 0 times 32. 0 times 16. 0 times 8. 0 times 4. 0 times 2. 0 times 1. If you do, that's what we have here. Once you do that, you will get your answer here. If you add them up, you will get 192. What are we saying? What is this 192? 192 is the decimal value of this 110000. So, for instance, let me do another example. Let's do another example. Let's say I have, okay, we have done this one. All right, we have just represented it this way and we got 192. Let's do another one. Let's have another binary value. You see this is that binary value. We put it, remember I said this value is constant. You just put it in form of a table. So I have this value 10101000. Convert it to decimal. All you need to do is you do the evaluation. This 1 times 128, 0 times 64, 1 times 32, 0 times 16, and then 0 times 4, 0 times 2, 0 times 1. Once you do you adding it up, you evaluate it, you're going to get decimal 168. How about another one? Let's say you have another one like this. Put it in the same table. You have 0, 0, 0, 0, then 1, 0, 1, 1. 1, 0, 1, 1. And you evaluate. If you do the same evaluation, just multiply it by these same values that are at the top there, the position value, you're going to get 11. So let me give you another example. Let's say I use another method to see whether I'll get 11. I pick this number 1, 0, 1, 1. Let's try another method. If I am to convert it to binary, the way you are taught in primary school or in secondary school, you say number the powers. If you're converted to decimal, sorry, you say 0, 1, 2, 3. You are numbering the powers. Is that not so? Then the next thing you do is you multiply it by the converting base. This is in binary. So it's going to be 1 times 2 raised to the power of 3 plus 0. Converting base is base 2, which is binary, times 2 raised to the power of 2 plus 1 times 2 raised to the power of 1 plus 1 times, sorry, okay, plus 1 times 1 times 1 raised to the power of 0. So if you do the evaluation, 2 raised to the power of 3 will give you what? 8. 8 times 1 is 8. Plus 0 times anything is 0. Plus 2 power of 1 is 2. 2 times 1 is 2. Plus 1 raised to the power of 0 is 1. 1 times 1, 1. So if you add or you add this one, you get the 11 that you have here. Okay, so the point I'm saying is that using this table is just like a short form of going through the rigorous way that we used to do it before. So using the table, if I have this binary number, I just put it in the table 0, 0, 0, 0, 1, 0, 1, 0. If I do the evaluation, 0 times 128, 0 times 64, times 32, times 16, times 1 times 8, 0 times 4, 1 times 2, 0 times 1. You see, if you do the evaluation, you will get 10. In a nutshell, what I wouldn't want you to forget is 3 things. Number 1, when you are using this table for conversion, this position value is constant. All right? And this position value is just 8 bits. 8 bits. And that 8 bits is because of the octets, the 8 bits that are in an octet. Okay, so 1 times 2 will give you 2 times 2, 4 times 2, 8 times 2, 16 times 2, 32 times 2, 64, and so on and so forth. That's how you got the 8-bit. So anything you put in the table, you multiply it by this position value, and then you evaluate. Okay, so how about you have decimal to binary? We have done from binary, you're going to decimal. Okay, this is, you have it in binary and you want to convert it to decimal. But in this case now, let's say you have a number in decimal and you want to convert it to binary. You have a value in decimal, you want to convert it to binary. You are using a similar table. So I will show you this method, and then I will show you another method we used to do in secondary school. Probably whichever one that suits you best is very, very easy. Now, here is also using a table. And you see the table brings us back to the same position value. The position value is telling us that there are 8 bits. And these 8 bits are the same value and they are constant. And then it says, start in the 128 position. Let's say you have a particular number you want to convert. We're going to use an example very soon. So you start, you do like a comparison. And the comparison you're doing is going to compare whether it is greater. It's just a decision making whatever you're going to do, whether it's greater or equal to. If it is greater, you put a particular value. If it is not greater, you put a particular value, and the value is either 0 or 1. That is all. So this table is just to say if you have a number you want to compare, you want to convert, maybe 128, you want to convert it. How do you convert it? That is just it. So it says start in the 128 position, and which is the most significant. The decimal number of the octet is equal or greater than 128, you ask the question. If the answer is yes, you record 1. But if it is no, you record 0. All right. And you see that if it is yes, you record 1, and then you go back and then do the next value. If no, the record a binary 0 in the 128 value and move to the 64-bit position value. So if it is not greater, you record 0 and then come here and compare the value with 64. If it is greater, you record 1. If it is not greater, you put 0 and you come back to the next value. If yes, record the binary 1 in the 128 position value and subtract 128 from the decimal number and move to the 64 position value. Repeat these steps through the position values. So let's see the example. In the example here, it's saying is 168 greater than 128. So let's come back here. If I want to pick, let's say 168, I now say is 168 greater than this one here? I do the first conversion and the table says yes. So you see, we say if it is yes, enter 1 in the 128 position. So here, this is the 128 position. So I'm going to put just record 1. And then I will subtract 128 once from the 168, which is the main value that I want to convert. So if I do the minus, I will get my answer as 40. Then I will carry this 40 and go back to the next phase. So I come back here. The next one is what? 64. Yeah. So I will say, is 40 greater than 64? If the answer, let me go back here. If the answer is no, where is it? Where are we? Okay. Is 40 greater than 64? This is what we are comparing. If the answer is yes, we will record 1. But the answer is no, we will record 0. So you see, the answer is what? No. So record 0 in the 64 position and move on to the next. So you see, I will record 0 here. Then I will move on. Is 40 greater than 32? So you see, because the answer is no, I'm not going to do any subtraction. Yeah? Okay, I see Samuel is raising his hand. Samuel, do you have a question?
No, it's a mistake. It's a mistake.
Okay, thank you very much. Okay,
No, thank you.
so if the answer is no, okay, if you observe that once the answer is no, I'm not going to do any subtraction like we did here. But the answer is, if the answer is yes, then we'll go and do subtraction. So the answer is no, then you just come, is 40 greater than 32? Then if the answer is yes, you enter 1. So anywhere we put 1, then we will do the subtraction. 40 minus the 32, and then we will now carry this, the remainder, which is 8, and then go back and then do the same thing under 16. If it is no, we put 0. Under 8, if it is 1, we will now do the subtraction, and we do that until we get these values. This is one method. to convert 168 to binary. So if we do convert 168 to binary, what did we get according to this? We got 1 0 1 0 1 0 1 0 1 0 1 0, then 0 0 0 0. Okay, so let's try another method. Then you can choose whichever one. Another method is just to put 168 here and you divide it by 2. Why are you dividing it by 2? Because you are converting it to binary. Binary is 2. Then you will record the remainders. Okay, so 2 into 168. How many times? We see 2 into 16 is 8. 2 into 8 is 4. Is there a remainder? No. So I'll put remainder 0. Then I come here again. 2 into 84. 2 into 8 will give me 4. This one will give me 2. Remainder 0. Is that not so? I come here again. 2 into 42 is 21. Remainder 0. 2 into 21 is 10. Remainder 1. 2 into 10 is 5. Remainder 0. 2 into 5 is 2. Remainder 1. 2 into 2 is 1. Remainder 0. And then 2 into 1, 0. Remainder 1. That's another method. So how are we going to get our answer? Our answer is going to take from down to up. This answer, the remainder. And what are the remainder? You see 1, 0, 1, 0, 1, 0, 0, 0. That is the same thing that we have here. So the whole idea is that you are converting from decimal to binary and then binary to decimal. So routers and computers only understands binary while human work in decimal. So it's important for you to gain a thorough understanding of these two numbering systems and how they are used in networking. So in your machine, all you are going to be entering is the values in decimals. You're not going to be entering your IP addresses in binary, no. But your knowledge of the binary will help you in the conversion. So if I have an IP address 192.168.10.10, how does the computer see it? It converts these numbers in decimal, it converts them back to binary. So 192 converted to binary will give me this value. 168 converted to binary will give me these values. The same as 10 and this. So this is the machine understandable way, and this is the human understandable way. That's binary. Now, how about hexadecimal? Hexadecimal are two words put together, hexa and decimal. Hexa means 6, decimal means 10. So we are looking at a base 16 number system. You see, binary is a base 2 number system, but hexadecimal is a base 16. So to understand IP version 6 addresses, you must be able to convert hexadecimal to decimal and vice versa, just as we did with the binary. Okay, and in the binary, we used it because it was IP version 4. IP version 4, so we see how you can convert from binary to decimal and decimal to binary. But here in IP version 6, you need to understand hexadecimal. Okay, so the hexadecimal is a base 16 numbering system that uses zeros to 9 and then A to F. So you see, numbers starts from 0, 1, 2, 3, 4, all to 9. The next one is what? 10, 11, 12, 13, 14, 15. Now, observe something. Anything that moves from 10 downwards is a repetition of whatever it is that is up here. 10 simply means 1 and 0, which is here. 11 means 1 and 1, which is here. 12 means 1 and 2. 13 means 1 and 3. Up to 15. So it's a repetition of what you have here. So in hexadecimal, you represent from 10 to 15 here with alphabets A to F. Okay, you represent it with alphabet A to F. So if I have numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then instead of 10, I'll say A, B, C, D, E, F. Now, the representation in A to F is only for your understanding. But what is behind it is number 10, 11, 12, 13, 14, 15. So in other words, the value of A in hexadecimal is 10. The value of B in hexadecimal is 11. The value of C is 12. The value of D is 13. The value of E is 14, and the value of F is 15. So generally, that is how hexadecimals are represented. So you can still convert them to binary. Okay, just as you have these decimal values, we have done conversion of decimal to binary. So if I have this decimal value, I'm converting them to binary. This is what I'm going to have. All right. So if I have 10 here, this is the conversion of 10 to binary. So it means that this same 10 is the same as A in hexadecimal. Now, IPv6 uses 128 bits in length. Every 4 bits is represented by a single hexadecimal bit. Now, this is to explain a small difference. In IP version 4, we said there are 32 bits, while in IP version 6, there are 128 bits. Second comparison, IP version 4 has 4 octets, 4 octets of 8 bits each. IP version 6, each octet is 16 bits. 16 bits of 8, we call it segments. 8 segments. So instead of having 16 bits of 8 binary segments, they decided to convert it to hexadecimal. All right, hexadecimal. So you see that in each segment, in IP version 6, this is segment 1, 2, 3, 4, 5, 6, 7, 8. Each segment. And in each segment, there are 16 bits. Look at it here. These are 16 bits of segments, binary. But you need to represent it in hexadecimal. And this is the hexadecimal representation. The question is, how then do we convert from this decimal to hexadecimal? Or how then do we convert from binary to hexadecimal? And the answer is very, very simple. All right. So I'm going to now show you a very simple way to do the conversion. Remember, I showed you how to convert from decimal to binary. Okay. And I've shown you how to convert from binary to decimal. Now, if I have a value I have converted to decimal, or let me put it this way, if I have a binary value, I want to convert to decimal. Let's say this binary value. Let's convert it to decimal. Then we now convert it to hexadecimal. And let's see what happens. So how do we convert it? This is 11010010. Convert it to decimal. All you just need to do is number the powers. 0, or you can use that table that we talked about, that position value table. All right. But if you don't want to use a position value table, you can say 0, 1, 2, 3, 4, 5, 6, 7. So I've done the numbering. The next thing is just to evaluate it by multiplying it by base 2, since it is in binary, which is base 2. So this is going to be here will be 1 times 7, 1 times 2 raised to power of 7. Okay. And then the next one, let me put it up here. 1 times 2 raised to the power of 7 plus 1 times 2 raised to the power of 6 plus this one is 0. So I'll just put 0 plus this one, 1 times 2 raised to the power of 4 plus everything, these two here are 0. All right, plus 0 plus 0 plus this one here, 1 times 2 raised to the power of 1. So let us evaluate it. 2 raised to the power of 7 will give us what? 128. 128 times 1 is 128. Plus 2 raised to the power of 6 is what? 64. 64 times 1 is 64. So I will say 64 plus this one is 0. Then this is 2 raised to the power of 4 is what? 16. 16 times 1 is 16. Plus this one is 0. Then we come to this last one. 2 raised to the power of 1 is 1 times 1 is 1, I guess. All right. So let's add it. 128 plus 64 plus 16 plus 1. What do we get? 8 plus 4.
The last one is 2, sir, not 1.
Okay, it's 2, right? All right. Okay, 2 raised to the power of 1 is 2. Correct. 2 times 1 is 2. So you are very correct. So it's 2 here. Let's put 2 here. All right. So 8 plus 4 is 12. 12 plus 6 is 18, if I'm not mistaken. 18 plus 2, 20. So I'll put 0, carry 2. 2 plus 2 is 4, plus 6, 10, plus 1 is 11. So put 1, carry 1. 1 plus 1 is 2. So you see, if I convert it to binary, from binary to decimal, I have got 210. Now, this 210, how do I convert it to hexadecimal? You see, the same formula I used to convert from, what do we call it? From decimal to binary by doing the division. We're going to use the same formula. Okay, let me just use it. This place is filled up. Okay, so let me just use it. So 210, let me just use it here. So if I say 210 divide by 16, the same formula, then I will record the remainder. Okay, now we will now ask ourselves, how many times does 16 go into 210? Okay, how many times does 16 go into 210? I guess it goes into it about, let's say 13. So let's see, if we say 16 times 13 will give us 208. Okay, 208. So remainder what? Remainder 2. Are we together? So 16 goes into 210 is 13 times. Remainder how many? Remainder 2. Because it's 208. So if we add 2 here, so remainder 2. Then we'll come here, 16. 16 into 13 is how many times? Is 0. Remainder what? Remainder 13. Remainder 13. So if I want to represent this, remember we say you carry your value from down up. That is your answer. So our answer is going to be 13 and then 2. But you see, if you write it like this, it's confusing. So you remember in hexadecimal, we said 10 is what? A. We said 10 is A, 11 is B, 12 is C. 13 is what? D. So which means here I'm supposed to write it as D2. That is supposed to be the answer, D2. So you see, I have converted from binary to hexadecimal. So you convert it from binary to decimal, then from decimal to hexadecimal. That's how you do your conversion. Okay? Now, we're done with module 5. You see, very brief. Module 6, once I'm done, or let me ask, do you have any question on it before we go to module 6? It is also another very brief topic. Okay. All right. Anyway, maybe once we are done, then I'll take all the questions. Module 6, data link. Now, in data link, we're going to look at the purpose of the data link, then topologies, then data link frame. If you remember, in our last class, we looked at the physical layer. The OSI model has layer 1 as the physical layer. The next layer after layer 1 is the data link. And that is what we want to be looking at. What is the purpose of the data link layer? The data link layer is responsible for communicating between the end devices network interface cards. Okay? And it allows upper layer protocols to access the physical layer, media, and encapsulate layer 3 packets into layer 2 frames. What are we saying here? We're saying that in the OSI model, layer 1 is the physical, layer 2 is the data link, layer 3 is the network layer. Layer 2 is the data link which we are talking about, and we're saying that it provides a platform where this layer 3 or upper layers are able to talk to the physical layer, especially the network interface cards. And at this particular layer, there are the key elements here is the MAC address, because you see that every network interface card has a MAC address. Okay, so it allows communication between devices based on MAC addresses. So there's always a source network interface card, which is MAC address, then the destination network interface card, which is also the MAC address. Apart from the IP address, the IP address is dealt with at the layer 3. Is at the layer 3. And you see the layer 3 in the IP address, the device that works on it is the router. And it uses it for basically routing purposes. So the layer 2, which is the data link, is the MAC address. And the device that functions at this layer is basically the switch. The switch functions at this particular layer. So in the MAC address layer, there are certain standards that we talked about that help to work together. So in these standards, we're going to see them very soon. In these standards, they define that the MAC address has two sub-layers. It has what we call the logical link control sub-layer, and then it has the media access control sub-layer. That is in the data link layer. The logical links control sub-layer communicates between the network software and the upper layers and the device hardware and the lower layers. So this guy functions based on the devices that are the top, which is the network, which is the layer 3. And then this guy functions based on the devices that are down, which is the physical layer. So the data link layer carries two major roles. Serves as an intermediary, provides the platform where upper layers can talk to each other, and then lower layers can talk as well. Okay, that is what the data link provides. So packet exchange between nodes may experience numerous data link layers and media transitions. At each hop along the path, a router performs 4 basic layer 2 functions. That is the router itself. What does it do? It accepts a frame from the network medium. Then it decapsulates the frame to expose the encapsulated packet. Then it re-encapsulates the packet into a new frame and then forwards the frame to the new medium. Remember, we talked about this encapsulation process. So imagine this, that you have a PC here. This is a PC, and this PC is connected to a switch. The switch is connected to a router, and this router is connected to maybe a server somewhere here. You see, this particular PC will send a message based on the MAC address, but the destination IP address is this particular server. So what we are saying here, if this PC sends this message, there will be encapsulation process that will take place. Once the encapsulation gets to this switch is a layer 2 device. So there will be a decapsulation. There will be a decapsulation up to layer 2, from layer 1 to layer 2. And then from this side again, there will be another re-encapsulation. The switch is going to re-encapsulate it because it's going to be another frame. Then when it gets to this device, there will be decapsulation on this interface because it is talking from MAC address to MAC address. Then once it decapsulates, it gets the IP address, does its routing process and discovers that the message is meant for the server. Then it does another re-encapsulation on this interface. And then before it gets to the server where the decapsulation takes place completely. So you see it starts maybe something like this, comes like this, then comes like this, then comes like this, comes like this, then comes like this. So it does encapsulation, decapsulation, encapsulation, decapsulation. So we are saying that at each hop, this is like a hop, this is like a hop, all right? At each hop, it does 4 of this. It accepts the frame from the network medium, decapsulates the frame to expose the encapsulated packet, and then re-encapsulates the packet into a new frame before it then forwards it. Now, who are these organizations or standards that we were talking about earlier? We have the IEEE standards. The IEEE stands for the Institute of Electrical and Electronic Engineers. And they are just like the body that sets standards on the manufacturing of some of these devices. Then you have the ITU. The ITU stands for the International Telecommunication Union. Then you also have the ISO. The ISO stands for the International Organization for Standardization. Then you have the ANSI, which stands for the American National Standard Institute. Let's look at topologies. Physical and logical topologies. The topology of a network is the arrangement and relationship of the network devices and the communications between them. There are 2 types of topologies used when describing a network. And we saw that at the beginning of, I think, module 1 or so. So we have the physical topology, and then you have the logical topology, right? So the physical topology shows the physical connections and how the devices are interconnected, while the logical topology identifies the virtual connections between these devices using device IP addressing schemes and things like that. Now, one technologies or one topologies also has its own types of topologies. All right. And when we talk about one topologies, we're talking about inter-network communication. So we have what we call the point-to-point communication or a topology, which is the simplest and most common type of one topology and consists of a permanent link between the 2 points. So you may have maybe a particular radio, then it's connected to another radio like this. This is point to point. Okay. And so sometimes it might be via SAT connecting to the internet, to the space before connecting and things like that. So that's a point-to-point topology. Then you have what they call the hub and spoke topology. It's similar to like a star topology where a central site interconnects branch through point to point. Okay. And the hub and spoke is like what we call point to multi-point. So maybe you have a particular router, and that router is connected to maybe another router, is connected to another router in another location, connected to another one, connected to another one, and so on and so forth. So this is like a hub and spoke. You can think of it like a bicycle. You know, when you have a bicycle, the rail of a bicycle is like the hub and spoke. So that's why it's called. Then you also have another topology called the mesh topology. And what this provides is high availability, but requires every end device to be connected to the other one. So in mesh, you have like the hub and spoke. This central one is connected to everyone, but you see others are not connected to it. So in the mesh, this guy is connected to this is connected to this is connected like this. You see, they are all connected at the same time. So this one is everybody is connected to everybody. So this is connected to this. This is connected to this. This is and that is it. So everybody is connected to everybody. That is the concept of a mesh topology. Okay. So this is like the example of the point to point. All right, you have the point-to-point topologies and directs two nodes. The nodes may share a media with other hosts. Because all frames on the media can travel to and from other nodes, point-to-point one protocols can be very simple. All right, this is another topology in the LAN technology that also shows star topology. This is like star topology. Uh, can we meet ourselves, or let me just meet everybody? When we're done, then now take it. All right. So so you see in the star topology, there is a hub at the middle, and everybody is connected. Okay. This is the extended star topology for the LAN. All right. So you see, it's like a star topology, but is extended. This is what they call the ring topology. And then this is what we call the bus topology. All right. So in the case of the LAN, these are like the other topologies we have. Now let's look at communications. We have what we call the half duplex and the full duplex communication. Half duplex allows one device to send or receive message at a time on a shared medium. All right. So sometimes you use it when you're using a wireless LAN technology and things like that. Or when you have what do you call it, this walkie-talkie. You understand this walkie-talkie, you have maybe the one that police use and things like that, or security agencies. So you have to press a notch and then say your own words, and you wait for the other person to respond. Okay, the two of you cannot talk at the same time. That's half duplex because the message goes one traffic at a time. Full duplex on the other side allows both devices to simultaneously transmit traffic, both sender and receiving at the same time. It's like your smartphone. All right. So if I pick my phone and I call someone, and then I can be talking, he's listening, he can talk with me. So both of us can argue at the same time because you are transmitting and receiving at the same time. So that's the concept of that one. And the concept of access control method talks about all nodes operating on half duplex as the contention-based access. All right. So they are competing for the use of the medium. So like we talk about, the example is like this wireless access point, and where you have multiple devices that are trying to connect at the same time. So if there is a collision at the same time, what happens is that this technology helps out. CSAMA/CA. It means carrier sends multiple access with collision avoidance. This is where it tries to avoid the idea of collision. All right. So that is that one. Now, we also have another one called the contention-based access method, CSMA/CD. All right. In this particular case is to detect collision. Is used by legacy Ethernet LANs and operates in half duplex mode where only one device sends or receives at a time, and uses a collision detection process to govern when a device can send, what happens when there is a collision. So it's a technology that helps the devices not to collide amongst themselves. So if somebody wants to send a message on the network, it has to listen to be sure that nobody has sent a message so that there will be no collision. But if for any reason, two of them sends message at the same time, they use what we call the back-off algorithm. They go back and count certain numbers randomly before they begin to retransmit or begin to resend. So that is what happens in that particular case. Data link frame. In the data link frame, it has the header, it has the data, and then it has the trailer. Okay. And data is encapsulated by the data link with the header and a trailer from the frame. So the header is the information that comes from the upper layers. Then you have the data itself. The header is information that is added by the frame. The data includes information from upper layers, which is like the headers of other upper layers, including the data itself. Then the trailer is like the one that takes care of the error detection. So that is how the frame is. So you see the frame has like the header, then the packet, then the trailer. In the header of the frame, it has what we call the start frame, and then it has the addressing. The addressing is where you have the MAC address, the destination MAC address, and the source MAC address, and things like that. Then it has the type, and then the type actually identifies encapsulated layer 3 protocols. Then it has the control, which identifies the flow control services that are running there. The data itself contains the payload that has been sent from the upper layer, which is like the network layer. Okay. Then under the section of the trailer, there is what is meant for error detection and determines whether there is an error in the message or not. So how does it address its layer 2? How does it do its addresses? So um, layer 2 is also referred to as the physical address, which is like the MAC address, and it contains in the frame header. Is used only for local delivery of a frame on the link and updated by each device as it forwards the frame. Okay. So for instance, this guy is generating a message for this destination. And so in the messages, in the addressing scheme that is going to be there, there's going to be a layer 3 packet, which contains the source IP address and the destination IP address. But for the layer 2, there's going to be the destination MAC address and the source MAC address. That is going to be added into the frame so that by the time it gets to this device, what do you think will happen? The destination MAC address here is going to be the destination MAC address of this router. So this router is going to do its re-encapsulation and put a destination MAC address of this router here. And then this router will do a re-encapsulation again and put a destination MAC address of this particular, what do they call it, server. But from here, what does not change is the destination IP address. So the IP address that is assigned by the sender is this is the destination IP address is the one that does not change, but the MAC address changes across the path depending on the devices or the hubs that it actually meets. All right. So the logical topology and the physical medium determine the data link of the protocol that is used. Sometimes you use Ethernet, sometimes you use wireless, sometimes you use point-to-point, sometimes you use HDLC, sometimes you use frame relay. I know some of this may be a little strange, but when we get to CCNA 3, we will talk a lot more about this. So this is where we'll draw the curtain for the end of module 6. So at this point, I'm sure we may have some questions. So I'm going to open the mic for your questions. So just a minute.